Hi everyone, and welcome back to this series of tutorials about application of machine learning using WEKA in power asset assessment. In the previous tutorial, we talked about controlled discharges. We talked about corona. We talked about dry surface and wet surface. Now we'll try to take it one further step and we'd like to actually monitor ceramic insulators. Now, ceramic insulators are, as we know, older in the network than the polymer insulators. And in North America, for example, we have around 150 million of those cap and pin insulators and long rod insulators and different forms of those ceramic, which could be porcelain or glass. Now, many of them, they have exceeded their life and they start to develop a crack. And this crack can lead to complete failure of the insulators. So we want to detect if there is a crack in the insulator. But crack is not the only source of possible discharge that will be detected by the acoustic sensor that we used, the same sensor we used in the previous tutorial. But also dry band arcing coming from polluted surface can also emit these ultrasonic signals. Now, if I have a physically damaged insulator, the action required is to replace the insulator. But if I have an arc coming from a polluted insulator, then the action could be like washing the insulators. Because for the arc to happen on a polluted insulators, there should be two combination of two things. There should be a conductive pollutant and humidity. Okay, so if we clean the insulator from the pollutant, then there will be no dry band arcing on the surface. So as you can see here, the actions are different, depends on the type of defect. Add to that, corona is also available in the network from different sources. Any sharp point, any strand that is damaged in the conductor, any damaged hardware in the overhead lines can generate corona, which also can be detected. So this is a three classification problem that we use for it, the same setup, exactly the same setup. So this is our sensor here. This is the acoustic sensor that will give us at the end of the day three frequency components. So it's the same feature vector, but now the only difference here, as I said, we have now one cap and pin insulator. So we have here a crack. We have here a corona. We generate the corona by having a thin wire wrapped around the cap. And then we have the polluted surface. Okay, so this is the setup. This is the our data. Now let's go to WEKA and let's do our classification. So this is our WEKA. We'll do the same thing. Go to the Explorer. Now we will open the file. So I have the file here. Now we need to change this to CSV. So this is my file. Open. So the classes we have called defect type. So we have corona 100 cases. We have surface crack 100 cases and polluted surface 100. So this is more of a balanced scenario where each case is 100. So we will go for the classification. We will use cross validation with tenfold. This is exactly the same thing that what we keep on doing using OR the classifier. So again, I will use the four classifier we used so far: ANN, SVM, KNN, and J48, and compare between them. So let's start with ANN. So this is our functions. We'll go for the multi-layer Perceptron. I will come here and I will select two. I will let me select one and see what will happen if I change the parameters a little bit. So let's say one, and let's start. Okay, So here we have an 84.7 accuracy, which is way less than the controlled case. Here the corona has 100%. So it was not misclassified with any of the other two cases. But when you look to the surface crack, the surface crack has true positive of the surface crack is 61%. Okay. And the polluted surface was 85%. Okay. So let's go here and change the hidden layer to 2, because we have a very good accuracy when you go from 1 to 2. So let's start. Okay, now it is 87%. Again, the corona is 100%, no misclassification. But now we have improvement in the true positive of the surface crack to from 61 to 76%, and the polluted surface is 87%. Okay, let's start or try another classifier. Let's do the SVM here and go start. Oh, okay. The SVM gives us a better result. It's 88.7%. Again, the corona is 100% and 77% for the surface crack and 89% for the polluted surface. So I can see here so far the corona is always 100%, but the problem is between the other two classes. Okay, let's come and select the KNN. So the KNN, let's use the default, which is KNN1. Let's start. Okay, now it is way less, 82%. But even though we have 100% in the corona. Okay, let's go here. Let's make it KNN3. Okay. And okay, classify. Okay, it's 85% improvement. Again, the corona 100%. And the problem mainly in the surface crack. Okay, let's do 5. Okay, start. 87%. So it's sort of saturated, but we are getting 81%, and again 100% for the corona. Finally, let me select the G48 and see if there is any difference. Start. It is 86%, and again the corona is 100%. Okay, so let's go back now to our presentation here. And let's see the results, all of them in one slide. So this is the results that we have. So the best we got so far is in the SVM. We have only 34 misclassified cases out of the 300. The ANN second 38, 39, and 41. I use KNN 5. Okay. So one important thing that we realized here, that all of them, they have 100% in the corona. And we need to understand why is that, why the corona specifically has this very high rate. I mean, the perfect rate, which is 100%. Okay, so let's go here and let's compare. So this is the visualization of the data. The x-axis is the 60 hertz. The y-axis is the 120 hertz. So these are the two feature vectors, the 60 and the 20. And here we have the classes. So when you look to our case that we have here, so you see here, this is the corona. And these are the two other cases, the surface crack and the polluted surface. See how much gap between this and this? So this is why for the corona, regardless of any classifier, you are getting perfect classification. However, when you look to the surface crack and the polluted surface, they are somehow, there is an overlap between them. Okay, and this is why we have the problem. Now, when you look for the controlled cases, it is somehow the classes, they are not actually overlapping. This is why we got 99% there. Here, the maximum we got is 88.6%. Okay, so first lesson we learned, when we move from a controlled case, where we control that type of discharge to more realistic case, you expect that the accuracy of your prediction will go down. Okay, because now we have more of a realistic problem, not very controlled problem. Now imagine if we want to go from this realistic problem to the field. Now we want to go to the field and take the measurement under the noise of the field. What do you expect to see? Okay, so we expect to see that even maybe the accuracy will even go down. Another observation here you can notice, in using the transformer data, ANN was giving us the best classification. With the controlled discharge, KNN was giving us the best, and now here SVM give us the best results. So this tell us something very important. I mentioned before that there is no perfect classifier. Always you have to try. Always you have to try different classifiers, and WEKA helps you to do that. However, Wiki has limited tuning on the classifiers. Now, when you write your own code in Python, you might be able to boost the result a little bit by playing with more with the parameters more, because you have more flexibility. But Wiki will give you some sort of like a general guidelines, a general idea about what is the expected accuracy. So with this, we conclude this tutorial. What's next? I'd like to discuss with you a very important aspect of machine learning, which is so far what we have done so far. I have certain data set. I split that to 90% training, 10% for the validation or the testing, and we do tenfold. Okay. Now, next time what I will be doing, I will have the transformer data, which is coming from utility A, and then I will get completely different data set from a different company. Okay, so this is different company, different conditions, different type of transformers, and we'll use this new data set as testing. So we will use the first data set as training, the second one as testing, and let's see what will happen in the results. So I'm sort of like doing some advertisement for the next one. So hopefully you will be able to join me. Bye everyone.